Welcome to another session of Easy Learn. Today, we will learn Part A of Class 10 Physics Chapter 2, Work, Energy, and Power. Are you ready? Let's start with a quick question to test your intuition. If you sit at your desk for 4 straight hours, reading your textbook and writing notes, are you doing work? In our daily language, we say yes. You feel completely exhausted. But in terms of physics, you did absolutely zero work. How is that possible? In physics, the term work has a very specific meaning. Let's look at the textbook definition of work in physics. Work is said to be done only when the force applied on a body makes the body move. That is, there is a displacement of the body. Think about pushing a stalled car, pedaling a bicycle, or climbing up the stairs. In all these cases, a force is applied and motion is produced. That means work is being done. But what if you push against a solid brick wall with all your might, or try to move a massive stone that just won't budge? You will get tired and sweaty, but because there is no displacement, scientifically, no work is done at all. Now, how do we measure work? It depends on 2 factors: the magnitude of the force and the magnitude of the displacement. Look at the textbook rule. The amount of work done by a force is equal to the product of the force and the displacement of the point of application of the force in the direction of force. Mathematically, when force and displacement are in the same direction, our formula is simple. W equals F times S. But what if the force and the movement are not in the same direction? Imagine pulling a toy truck with a string. You are applying the force at an angle through the string attached to the toy truck. But the toy truck is moving along the floor at an angle to the force. When this happens, you can calculate the work done in 2 ways. You can find the component of displacement along the force, or you can find the component of force along the displacement. Both methods give the exact same result. Let us look at the first method. Imagine a constant force F acts on an object along the line AB. This force moves the object up a ramp from point A to point C. The actual displacement of the body is AC, which is S. There is an angle theta between the force and the displacement. To find the displacement along the force, draw a straight line down from C to AB. This creates a right-angled triangle, ABC. The component of displacement in the direction of force is the line AB. Therefore, work done equals force times AB. In this triangle, cosine theta equals the base divided by the hypotenuse. That means cosine theta equals AB divided by S. If we rearrange this, AB equals S times cosine theta. Now, substitute this back into our work formula. We get work done equals F times S times cosine theta. So work equals force times the component of displacement. Now, let us look at the second method. This time, we calculate the component of force along the displacement. Let the line PA represent the total force F. The part of this force pushing along the ramp is the line NA. Therefore, work done equals NA times the displacement S. Now, look at the new right-angled triangle PNA. In this triangle, NA equals F times cosine theta. If we multiply this force component by the displacement, we get the same result as earlier. Work done equals F cosine theta times S. So work equals the component of force times the displacement. In conclusion, work done is always the force multiplied by the displacement multiplied by the cosine of the angle between them. In vector physics, force and displacement are both vectors. Work is the dot product of these two vectors. Because it is a dot product, work is a scalar quantity. It has a size, but it does not have a direction. Now, let's explore 3 very important special cases based on this angle theta. Case number 1. What if the displacement is exactly in the direction of the force? Here, the angle theta is 0 degrees. Since the cosine of 0 is 1, the formula simplifies to its maximum value. W equals F times S. This is called positive work. For example, consider an object falling freely from point A to point B through a height h. If m is the mass of the object, the gravitational force acting on it is mg, and its displacement is h. Since both the force of gravity and the displacement are in the same direction, the angle theta is 0. Therefore, the work done equals force times displacement, which simplifies to mg multiplied by h. Case number 2. What if the force is completely perpendicular to the displacement? This means the angle theta is 90 degrees. Because the cosine of 90 degrees is 0, the total work done drops to absolutely 0. For example, consider the centripetal force acting on a body revolving along a circular path. In this case, the force acting on the body is directed toward the center, but the displacement of the body is tangential to the path at all instants. Hence, the work done by the centripetal force on the body is 0. This is why kinetic energy, and hence speed of the body, does not change although a force acts on it. In physics, there are 2 specific situations where the work done by a force is exactly 0. The first situation is when there is no displacement, meaning S equals 0. The second situation happens when the displacement is perpendicular to the direction of the force. That is, theta equals 90 degrees. Now, let me ask you a tricky question. Imagine a runner sprinting at full speed around a circular track. He starts at point A, power through the entire loop, and cross the finish line right back at point A. What is the net work done here? The answer is 0. Wondering why? It all comes back to the first situation that we just learned. Because the runner ended up exactly where he started, his net displacement is 0. And in physics, if there's no net displacement, the net work done is also 0. Case number 3. What if the displacement is in the exact opposite direction to the applied force? When this happens, the angle theta is 180 degrees. Since the cosine of 180 degrees is -1, our formula becomes W equals minus F times S. This is called negative work. This usually happens when a force actively opposes the motion, or tries to stop a moving body. For example, think about friction. When a box slides across a floor, the force of friction acts in the opposite direction of the movement, doing negative work. Another great example is throwing a ball straight up into the air. While the ball travels upwards, the force of gravity pulls it downwards. Because the movement and the force are opposite, the work done by gravity during this upward journey is negative, calculated as W equals negative mgh. Now let me ask you another trick question. Imagine you drop a ball straight down from the top of a flight of stairs to the ground. Next, you carry a second ball down by walking down the stairs. Finally, you take a third ball down to the ground using an elevator. In which of these cases does gravity do the most work? The answer might surprise you. Gravity performs the exact same amount of work in all three cases. Why? The gravitational force always acts vertically downward. The net displacement in the direction of this force is simply the height, h. Regardless of whether the ball drops straight down, is carried down the stairs, or travels in an elevator, this vertical displacement h is constant. Therefore, the work done by gravity is always exactly mgh. So far, we have learned about the work done by a constant force. But what happens if the force is not constant and changes as the object moves? This is called a variable force. To calculate work in this situation, we use a force displacement graph. We plot force on the vertical y-axis and displacement on the horizontal x-axis. The total area enclosed by the variable force line and the x-axis gives the work done. For example, let's say force F is directly proportional to displacement S. Then, the graph of force against displacement is an inclined line. Let's call this line OA. The area enclosed by OA and the x-axis forms the triangle OAB, which is equal to half of force times displacement. So in this case, work done W equals to half times F times S. Now, let's talk units. In the SI unit system, the unit of work is the joule, abbreviated as capital J. 1 joule of work is done when a force of 1 Newton moves an object through a distance of 1 meter in its own direction. If you're dealing with massive amounts of work, we use bigger units, like the kilojoule, megajoule, or gigajoule. In the CGS system, the unit is the erg. 1 erg is when a force of 1 dyne moves a body by 1 centimeter. How do they compare? Well, 1 joule is equal to 10 to the power of 7 ergs. Now, let's step into our next major topic, power. Imagine 2 people doing the exact same work, but one finishes in 10 seconds and the other takes 60 seconds. Who spent more power? To understand this, let's get to the textbook definition of power. The rate of doing work is called power. It tells us how fast or slow work is being completed, while work focuses strictly on force and distance without caring about time. Power depends entirely on time. We calculate power by dividing the total work done by the time taken. Power, P, equals W over T. If a machine finishes a job in less time, it has more power. Like work, power has no direction, so it's a scalar quantity. Now let me ask you another question. Imagine 2 coolies, A and B, lifting identical loads to the roof of a bus. Coolie A takes 1 minute, while coolie B takes 2 minutes. If the power spent by coolie B is P, what is the power spent by coolie A? Since they lifted the same load to the same height, they did the exact same amount of work. But because coolie A did it in half the time, coolie A spent twice the power of coolie B. There is also a clever shortcut to calculate power when an object moves at a steady pace. We have learned that the formula for power is work done divided by time. But work equals force times displacement. So we can rewrite our power formula as force multiplied by displacement over time. And what is displacement divided by time? It is average velocity. Therefore, power can also be easily calculated as force multiplied by average velocity. P equals F times V. Now, let's look at the units of power. The SI unit of power is the watt. It is abbreviated as capital W. 1 watt of power is spent when 1 joule of work is done in exactly 1 second. That means 1 watt is equal to 1 joule per second. Bigger units of power are kilowatts, megawatts, and gigawatts. And smaller units of power are milliwatts and microwatts. In the CGS system, the unit of power is ergs per second. 1 watt equals 10 to the power 7 ergs per second. In mechanical engineering, largely used unit of power is horsepower. 1 horsepower equals 746 watts. Now, let's learn what energy is in the language of physics. Whenever work is done, there is always a transfer of energy. For example, when you push an object across the floor, you use the energy stored in your muscle cells. This energy is transferred to the object as kinetic energy. When you stop pushing, the object eventually comes to rest. This is because its kinetic energy is lost as heat energy due to the frictional force between the object and the floor. If work is done on a body, its energy increases. If work is done by the body, its energy decreases. Therefore, we can define energy like this. The energy of a body is its capacity to do work. Because it is directly linked to work, energy is also a scalar quantity. Basic units of energy are same as that of work, joules in SI and ergs in CGS. Bigger units of energy are watt-hour and kilowatt-hour. It is typically used for measuring electrical energy. 1 watt-hour is the energy spent by a source of power 1 watt in 1 hour. 1 watt-hour is equal to 3,600 joules, or 3.6 kilojoules. 1 kilowatt-hour is the energy spent by a source of power 1 kilowatt in 1 hour. 1 kilowatt-hour is equal to 3.6 megajoules. When dealing with heat energy, we use the unit calorie. 1 calorie is the heat energy required to raise the temperature of 1 gram of water from 14.5 degrees to 15.5 degrees. That is, by 1 degree Celsius. To tie it all back to our main unit, 1 calorie equals roughly 4.18 joules, and 1 kilocalorie equals 4,180 joules. But what if we zoom all the way down into the subatomic world? The energy of tiny atomic particles like electrons is so incredibly small that measuring it in joules wouldn't make sense. Instead, we use a unit called the electron volt. It is abbreviated as EV. 1 electron volt is the energy gained by a single electron when it is accelerated through an electrical potential difference of 1 volt. In terms of joules, 1 electron volt is an unimaginably tiny fraction. 1 electron volt is equal to charge of 1 electron multiplied by 1 volt. This equals 1.6 times 10 to the power negative 19 coulomb multiplied by 1 volt, which is just 1.6 times 10 to the power negative 19 joules. With that, we have completed part A of this chapter. Now, Let me ask you an interesting problem for you to solve. A conveyor belt sits at an inclined angle of 30 degrees to the ground. It must move a 1,200 kilogram load 60 meters up the incline in 12 seconds at a constant speed. Assume that the system is completely frictionless. Calculate the average power output of the conveyor belt's motor in kilowatts. Here is the clue. Conveyor belt is working against gravity. You have learned that gravitational force acts vertically downwards. Also, you have learned how to calculate power from work and time. Let me know your answer in the comment section. That brings us to the end of this session. Please remember to like, subscribe, and share your thoughts in the comments. Thank you so much for watching, and see you next time. Bye.